Okay, so now I want to give finally this theorem 1.1 of IUT4. So this is this thing where he uses faithfully flat descent to show a certain inclusion here. So this is a comparison of, let me clean this up a little bit, of this tensor packet of this tensor packet of OKI and OL. So I is equal to 1 up to m. So here we have a tensor product of rings of integers of p-adic fields over the p-adic integers. And then here, this was, so here, let me just remind you that OL, well, this was a direct sum of OL psi for size like this. And here, we're using that, that if we take this tensor product here, Km, this was a direct sum of L size for psi, a bunch of embeddings here. Okay, so so we take this tensor product of fields that breaks up by the Chinese remainder theorem into a product of fields, or direct sum of fields, doesn't matter. Then we take the integers of that, and then we take the direct sum of all those integers. Okay, so this is kind of the direct way of doing this, and then there's and so by the way, that this thing here, OL, is actually the integral closure of okay, let's call this one T. It's the integral closure of T in its total ring of fractions. That actually makes sense, right? Even though these aren't domains, you just localize at all the non-zero divisors. And then we also have that the field of fractions is the tensor product of these things. So if we were going to do this abstract field of fractions construction, we would get what we have here. So this OL notation it's okay. First of all, there's this ad hoc definition as a product, but it's actually the ring of integers. Okay, so before we get started in this proof, we need to give ourselves some reminders. So the first reminder is about the algebra structure for OK. So OL is a T algebra. T is this tensor packet here. And let me explain how this works. So the embedding decomposition of say the tensor product of fields or or the ring of integers, right? So it gives so the embedding decomposition gives that OL is this direct sum of OL size. So we've been calling this thing L, by the way. That's why we're calling it OL, right? And this is over tuples, where okay, so we have this thing, and if this thing is from T to OL, is the algebra map. Okay, we can write it as the following. So we can write it as, it goes phi A1 tensor up to AM. So it's equal to psi 1 A1 psi m AM. Okay, and this runs over a suitable collection of representatives of the embeddings. In the future, we will call this thing, for each component, phi sub psi of A1 tensor AM. So this is the component. Okay, so that's the first thing that we wanted to do, that we need to remind ourselves, is this algebra structure. The second thing that we need to remind ourselves of are the idempotents. Okay, and then what do? We took QP bar tensor over K1, and then we tensored it with this tensor product of fields. Okay, so this thing here was QP bar, and then we adjoined a bunch of variables. So this is the way we like to think about this tensor packet after we base change. Okay, so where so we have this. Okay, so of this thing. Okay, so in this notation here, we're thinking that OKI is ZP adjoin alpha of I. So these are integral, a monic integral extension. This is possible for local, for extensions of the p-adic integers, and the Fi are the integral minimal polynomials of the alpha i's. Okay, and so so here's the idempotent formula. It says that that we have the following, that G psi. So this is equal to a product from I is equal to 2 up to M. So here we're again selectively tensoring up to K1. So this is why this indexing starts at 2, but we could just as easily do this, everything I'm doing now with a different component. It would just be more cumbersome to write here. Okay, so then we have 1 over Fi prime psi I alpha I, like so. Okay, so these were the idempotents. Okay, so the two things. We have an algebra structure, which uses the embeddings. So to get the tensor product to act on this ring of integers, we use the embeddings. The other thing that we do is that we know what the idempotents are, and the big connection with the different is these denominators here. Okay, so the different of a local of these the different ideal is yeah. So let me just write that here. So the different ideal of k over qp, or the ring of integers of k over the p-adic integers, is generated by f prime of alpha, if alpha is a generator and f is its minimal polynomial. It doesn't necessarily need to be Eisenstein. It still works. Okay. An easy proof of this is to use a description of the different via the annihilator of the Kähler differentials. Okay. All right. So okay. So now what? Now we state the theorem and we prove it. Okay. So here's the theorem. Oh, what the heck? Okay. Here's the theorem. Okay, so we're gonna let K1 through Km be p-adic fields. So finite extensions of QP. Okay, so there are going to be finite extensions of QP. Okay, we're going to let T equal the tensor packet. Okay, and we're going to let L be the total ring of fractions of T, which is also equal to the tensor product of the fields. And now the tensor is over the p-adic integers. Okay. Okay. So if beta is equal to the following element, 1 tensor f prime of alpha 2 tensor f prime of alpha m. So this is f2 fm, where we're writing that O of ki is zp adjoin alpha of I with minimal polynomial monic polynomial fi of x in zp of x. Then beta is an element of T this colon ideal of OL. Okay, that is beta dotted with OL is contained in T. Okay, so let me say a little bit about why I'm writing this. Is that here, this is actually the object we're interested in, this colon ideal. This is like the conductor, I guess, and this comes up in the study of Gorenstein rings and things. So this is something we care about a lot. Okay, and we just have one particular element of this that we're going to use, and maybe it's smarter to study that thing in general, or find something else completely different, right? Okay, so now we're going to do this. We're also going to apply faithful flatness. Okay, and so when you do an extension of p-adic fields, they're always going to be faithfully flat, and so you'll see how faithful flatness works if you've never seen it before in the application of the proof. Okay, so and we'll just start it right now. So proof. Okay, so in view of faithfully flat descent, okay, or faithful flatness. I guess we don't need to say descent because we're not really. We'll say faithful flatness. So faithful flatness, it is enough to show the following. That if I take, so here's the ring of integers in the algebraic closure of QP, OK1, this is an OK1, 1. Okay, beta OL, this multiplication again is via that that map. Okay, this is contained in, okay, then we just base change again. Okay, so then OK1T. Okay, to show this inclusion here, it's the same thing to show this. So after we apply this functor. Okay. Okay. So okay. So we use the so we're going to introduce some notation. So we will use the notation. The following notation, that OL bar is well, you just take OL and you base change it. And we're tensoring over K1. Okay, and then we're going to use T bar. So this is the ZP bar OK1 T. Okay, so we're going to use these two notations. Okay, and so so using our definition of embeddings, so using our embeddings, direct sum decompositions. So we have the following. Formula. So it says ZP bar tensored over OK1 beta OL. So this is beta bar OL bar. Okay, so let me explain this a little bit. So here, we're beta bar. Here, beta bar is the following. It's the sum over these guys in this this collection of presentations. Okay, and now I need to do something here. So I need to use this to be normalized, and normalized in the sense of the video, so that normalized ones will correspond to collections of roots of the monic polynomials from 2 up to m, right? Okay, and then we're also going to use the presentation. We're going to use that notation again for the unipotents. Okay, so this is what we have here. So yeah, the action of beta on OL looks the following way. Okay, so yeah, so this is like I guess like the external multiplication, and this is like, so this is like the internal multiplication here. So this is as an OL bar module. Okay, or an OL module even. All right. so we want to note that the following is true, that so we look at the component corresponding to this embedding, right? And I'm just going to write down the definition of beta again. So here we have F2 prime alpha 2. Okay, this is our fixed one, right? Pre-embedding it anywhere. Okay, so we have all these alphas, and we're going to take this thing, and now we're just apply the homomorphism property. So this is going to be F2 prime psi 2 alpha 2. Okay, and then we have Fm prime psi m alpha m. Okay, so for psi is psi 1 up to psi m in this collection of embeddings. Okay, in particular, we're going to normalize it so that psi 1 is equal to the identity on K1. All right. Okay, so here again we're viewing K1 as embedded in the algebraic closure. Okay, so this is what we have. And so what else? So the other thing that we'll use, so we will use this following presentation for the idempotents. And now I'm going to write it out in terms of the embeddings. Okay, Fi, Xi bar. Xi, the bars will again denote that I'm considering things in the quotient. Okay, and then I have 1 over Fi prime psi I alpha I. Okay, so this is what we have. And so psi again runs like this. And so we're going to use this presentation. And so this is an element of 1 over, and notice what the denominator is. The denominator is this thing exactly. So beta here, and then I'm going to have ZP bar, okay, X2 bar, XM bar, and this is just the same thing as saying, you know, that this is this denominator with this T bar here. Okay, so now we've set up everything, and we just check that everything performs as advertised. So now we just check. Okay, and so what do we check? So if X is an R bar, right, it has the form, well, the X looks like a sum from psi and this big thing here of X psi G psi, like so, for X psi in ZP bar. Okay, so what we have is we have the following. So we have beta bar times X. Okay, now we just write everything out. We're going to use that idempotents are orthogonal. Okay, so this is here, beta G psi. Okay, maybe I should go back and stop for a second and say, this is exactly where we're using that the idempotents, or sorry, that the embeddings are normalized, right, to get this whole thing to work. Okay, so okay, so now this is going to be the sum, and then we'll write this like so, XC GC. Okay, and so this thing here, so when these multiply, if these two things are not equal, it's going to be 0. Okay, and then if they're the same, they're going to get a G squared, since in idempotent G squared is equal to G. Okay, so this will be the sum of just a single psi now, because they all got killed. Phi psi, beta, X psi, G psi. Okay, and now we have this times this. And this was exactly the denominator. Look, here. This is the denominator. Okay, so so this thing here is an element of T bar, right? Since so this line uses orthogonality, right? And then this line, this is since you know, phi psi of beta times G psi is an element of T bar. Okay, that's what we want to show. Okay, and so, all right, and that's it. And so let me make some remarks. So remarks. Okay, the remark again is that this theorem has nothing to do with K1. Right? So we can choose, you know, we can choose K1 or Ki to make the equality tightest. Make the inequality best, right? Okay, and yeah. So I guess we want beta to be p-adically largest, okay? And then the lemma that we have is that okay, so now, so I guess I wanted to say how this relates to the different, so because we're going to apply this in the context of the different later. So for OK is equal to ZP alpha, right, with minimal polynomial, f of x and ZP of x, so this is monic, right? Then and this always can be arranged. The different of OK over ZP is equal to f prime of alpha. I should say that, so what should I say? I should say that, okay, sometimes we do care so sometimes we use a different presentation here where we take an unramified extension and then we do some sort of Eisenstein extension. And that's useful in relating this to the ramification indices. So there's more than one presentation of these rings of integers that we want to use in practice. So okay. Anyway, there's a proof of this. Okay, so we'll use that this different. Oh my God, there's so many. Okay, annihilator. Okay, here. Okay, I've got something crazy. Not crazy to tell you. So okay, the Stacks project. Oh man, I had the tag written down here. Anyway, the Stacks project has this crazy general definition of difference if you feel like, you know, having a good time. You can go to the Stacks project and look up their difference and discriminants section. And so it's like based off of stuff that Kuntz did, and so it's kind of interesting. I didn't know that you could go so crazy with difference. Okay. So we use this here. So yeah, that made me think like maybe that you can do this whole thing like in, not have to do difference component wise, but like do it for the tensor product just at once. But I'm not that good at that stuff. Okay, so so we use this different. Then then OK looks like ZP x mod f of x and omega of OK mod ZP. We should really be using lowercase omegas apparently. Okay, so is generated by dx with the relation f prime of x dx is equal to 0. Okay, so yeah, so that's what's going on. Okay, so yeah. So let's think about like what's going on. One last thing. Let me just think about what's going on here because it's kind of like trippy when you think about it. Okay, so here, this thing is not necessarily a direct sum. Okay, so it's there's no idempotence. This is idempotence, right? And so this thing breaks into a direct sum here. So it's like sandwiched between two things that break up, right? And I guess this is possible, right? So this is actually an ideal in here. It's an ideal, and it's a T module, right? And so that's kind of weird, right? But it's and I guess you can have two submodules, two ideals in a ring, which as modules are in direct sum with each other, where and so that can happen. You just need to make sure that like the two ideals. So if you have I and J, and there are sub ideals of a ring R, then you just need to make sure that I times J is 0, right? And so then and that yeah. So then you can have the sort of thing that this is an example of. So it's not so crazy. Okay. Cool. I'm gonna that's all I'm gonna say about that.